Okay, so 2.32, we're asked to derive equations 2.170 and 2.171. For reference, these are the respective transmission and reflection coefficients for the finite well, and we're going to define them real quick as b being equal to I times sine 2LA divided by 2KL times L squared minus K squared times F, and F being equal to bottom being cosine 2LA minus I times K squared plus L squared over 2KL multiplied by sine 2LA, and then at the top we have e to the negative 2IKA multiplied by a. So our goal is to get these two from the finite well. Because they did not, Griffiths did not derive this, and he left it as an exercise for us. So since we're looking at transmission and reflection stuff, we're going to use the scattering states. So for the scattering states, the general wave function, as we've defined so many times already, is a times e to the ikx plus b times e to the negative ikx when x is to the left of the well. Then we have c times sine of lx plus d times cosine of Lx inside of the well. And then we have f e to the ikx to the right side of the well. So from this point, we can instantly start defining boundary conditions. So we have continuity at each of these boundaries, and we also have continuity in the derivative. So let's start with continuity at x equals negative a. So we have a e to the negative ika plus be to the positive ika, because x is equal to negative a and it causes negative to cancel. This has to equal c times sine of negative la plus d times cosine of negative la. And we can then take advantage of odd and even functions via sine and cosine. Cosine of negative la is even, so it's exactly the same as cosine of positive la. In contrast, sine is odd, so sine of negative LA is equivalent to negative sine of LA. So we do this. Next, we do the continuity of its derivative, which is going to be IK multiplied by a times e to the negative IKA minus b times e to the IKA. And this is going to equal, let's see, L multiplied by c cosine of negative LA, which just becomes positive LA because cosine's even, and then subtracted by d sine of LA, where sine it's originally plus, no, actually it's minus sine negative LA, so this becomes a positive, like this. Is that correct? Yes. Okay. And then for continuity at x equals positive a, we have c times sine LA plus d times cosine LA being equal to f e to the IKA. And then we have the continuity of the derivative, L times c times cosine of LA minus d times sine of LA is equal to IK times f e to the IKA. Let me just double check that's correct. Yes, that is correct. Okay, so from this point, it's just a matter of solving this system of four equations and getting b and f, so that's what we're going to do. Okay, so we're going to solve this system by using the hint that we're given. So it says to use equations 2.168 and 2.169 to solve for c and d in terms of f, and we're given the resulting answers here. So 2.168 and 2.169 are these two expressions. Whoops, that's a horrible line. They are these two expressions. So we're going to take these and we're going to solve c and d in terms of f. So let's start by solving for c. So I'm going to use this expression, and whoops, sorry about the sudden mic bump. I'm going to use this top expression. I'm going to solve for c. So we're going to say, okay, I can take equation, so this is equation 1, this is equation 2. I'm going to take equation 1, I'm going to say c sine times LA is equal to f e to the IKA minus d cosine times LA. From that point, I can then say c is equal to f times 1 over sine LA times f, or not f, times e to the IKA subtracted by D times cosine LA over sine LA. Then I can plug it into the bottom expression. So we're going to plug this into equation 2. And what we get is then, let's see, L multiplied by F times cosine LA over sine of LA times e to the IKA minus D times cosine squared LA over sine LA. And this is equal to IK F e to the IKA. Oh, you know what? I forgot to add the final term here. There's supposed to be another subtracted by D sine LA. Okay, from this point, we can move the L over. So what we have is then, let's see, negative D cosine squared times LA over sine LA minus D times sine LA is going to equal IK over L times F e to the IKA minus F cosine LA over sine LA e to the IKA. Let's do some. Let's do a little bit of distributive property. So D is going to equal, and I'm going to move the negative over to the other side. So D multiplied by cosine squared LA over sine LA minus sine LA is going to equal, let's see, F times e to the IKA multiplied by cosine of LA over sine of LA subtracted by IK over L. Yes, okay. And from this point, I want to combine a few terms. So let's see. I can say this can be equal to cosine squared LA minus sine squared LA over sine LA. And this is going to equal F e to the IKA multiplied by, you know what, I'm just going to copy paste this. And if I move this over, this is going to give me that D is equal to F e to the IKA, and then multiplied by, let's see, sine, that cancels out, so we have cosine squared LA minus, no, hang on, sorry. We take the reciprocal of this to move it to the other side, sine, so we have cosine LA over cosine squared LA minus sine squared LA. And then we are subtracting by IK over L multiplied by sine LA over cosine squared LA minus sine squared LA. And you know what? I just realized I did something wrong here. This is supposed to be a positive because I moved out a negative D. So this is cosine squared plus sine squared, cosine squared plus sine squared, cosine squared plus sine squared. In which case, this simplifies much more. This is just going to be D is equal to F e to the IKA, and then we take advantage of the trigonometric identity that cosine squared plus sine squared equals 1, giving us cosine LA subtracted by IK over L times sine of LA. So this is our expression for D. Now let's do the same thing and solve for C. So we plug back in to equation number 1. So let's do this final one in blue. So we have equation number 1 telling us that C times sine LA plus D times cosine LA is equal to F e to the IKA. So then we plug in D and we get that C times sine of LA plus, let's see, F e to the IKA, and then we're multiplying cosine LA into this, so this is cosine squared LA minus IK over L sine LA cosine LA, and this is equal to F e to the IKA. If we then isolate C, then we have C sine LA is equal to F e to the IKA 1 minus cosine squared LA plus ik over L sine LA cosine LA. And from here, I divide everything by sine, so C is equal to fe to the ika times 1 over sine LA minus cosine squared LA over sine LA plus ik over L cosine LA. Let's see. We can take advantage of a trigonometric identity here. I just don't remember what exactly it is, so give me 1 sec to search up the trig identity for what 1 minus cosine squared actually equals. Well, okay, so cosine squared plus sine squared equals 1. So 1 minus cosine squared is then equal to sine squared. So this is equal to fe to the ika times sine squared LA over sine LA, because I combined these two fractions. 1 minus cosine squared LA at the top becomes sine squared LA. These two canceled out. I just get sine of LA added with ik over L cosine LA. And let me just double check that this is correct. Sine LA plus ik over L cosine LA e to the ika times f. Okay, yeah, this is correct. So with that, we finish the first step. We have solved C and D in terms of f. Now let's move on to the next one. Okay, so now that we have C and D, we are asked to plug these back into equations 2.166 and 2.167. So for reference, those are the continuity equations in terms of A. So we have the 2.166 right here, and we have 2.167 right here. So if we plug these in, what we're going to get is, let's see, let's move this down like this. So the first expression is going to give us AE to the negative IKA plus B times E to the IKA is equal to, let's see, negative, okay, so FE to the IKA multiplied by, and then we're going to multiply everything by negative sine LA. So negative sine squared LA minus IK over L sine LA cosine LA. And then we're going to add D cosine LA. So we're going to add FE to the IKA and then multiply everything inside here by cosine LA. So cosine squared LA minus IK over L sine LA cosine LA. And then for the second expression, this is going to give us IK times AE to the negative IKA minus B E to the IKA. And you know what? I'm going to move the L over to this side. So IK over L is going to equal, and then we have C cosine LA. So FE to the IKA times sine LA cosine LA plus IK over L cosine squared LA. And then we're adding D sine LA. So plus FE to the IKA times sine LA cosine LA minus IK over L sine squared LA. With that. And now we can just simplify these. So let's see. The first expression is going to become number 1. We have AE to the negative IKA plus BE to the positive IKA being equal to FE to the IKA multiplied by negative sine squared LA plus cosine squared LA. And then we are subtracting IK over L times 2 sine LA cosine LA. And for number 2, we have IK over L times AE to the negative IKA minus B E to the positive IKA being equal to FE to the IKA times, let's see, 2 sine LA cosine LA, and then plus IK over L multiplied by cosine squared LA minus sine squared LA. And immediately we can take advantage of double angle identity. So let's see. First off, this term right here is just sine of 2LA. So we can replace that. Same thing over down here. This is just sine 2LA. Then let's see. So cosine squared minus sine squared is cosine of 2a. So this is just cosine 2a. Or 2LA. Similarly, negative cosine of 2LA is going to be cosine squared, is going to be sine squared. No, this is negative sine squared plus cosine squared. So this one is also cosine of 2LA. And from that point, let's see, let me just double check that this is correct. F e to the ika cosine 2LA minus ik over L sine 2LA. F e to the ika sine 2LA plus ik over L cosine. Yes, okay, this is correct. So now we have A and B purely in terms of F. We can just solve this resulting system and get the sort of coefficients. Okay, let's start by solving this first equation for A. So in expression 1, let's do this in red. In expression 1, we have that A e to the negative ika is going to equal negative B e to the ika plus F e to the ika times cosine 2LA minus ik over L sine 2LA. So then I can say that I can plug this into expression 2, and this is going to give me that, let's see, negative B times e to the ika plus F e to the ika times cosine 2LA minus ik over L sine 2LA, and then subtracted by B e to the ika is going to equal, I'm going to move the ik over L to the right, this becomes L over ik times F e to the ika sine 2LA plus ik over L cosine 2LA. Close this off. Then we move stuff over, so we get that negative B times e to the ika, or in this case, negative 2b, because there's two terms and we're combining them, so negative 2. This is going to equal, let's see, F e to the ika times L over ik sine 2LA plus L over ik cancels ik over L, so cosine 2LA minus cosine 2LA plus ik over L sine 2LA. Then the cosine 2LA's cancel, we get negative 2b e to the ika is equal to F e to the ika times, let's see, if I want to combine these, this is going to give me L squared over ILK sine 2LA plus ILK, and then multiplying ik at the top, it gets negative k squared, so I'm going to turn this positive to a negative sine 2LA. Okay, then this is going to give us negative 2b e to the ika is equal to, let's see, F times sine 2LA over IKL e to the ika times L squared minus k squared. Then I add a negative at the front. Yeah, so then this is going to become b times e to the ika is equal to f, and then I can move the I to the top, add a negative, so negatives cancel out. So this is going to be I over kl times, and then add a 2 at the bottom because I'm moving the 2 over. So I over 2kl times sine 2la times l squared minus k squared times e to the ika. And with that, if we look back above, actually, you know what? I need to cancel out the e to the ika first. B is then equal to I times sine 2la over 2kl times l squared minus k squared times f, where I cancel out the e to the ikas. And if we look above, this is it should be, yeah, this is exactly what we get. So with that, we have verified B. Now let's move on to F. So now that we know what B is, we plug this back into expression 1. And let's write this in green. So we have then A times e to the negative ika plus, let's see, I sine 2la over 2kl, l squared minus k squared, f e to the ika is equal to f e to the ika times cosine 2la minus ik over l sine 2la. Move stuff around, we get a e to the negative ika is equal to f e to the ika multiplied by cosine 2la minus ik over l sine 2la minus I over 2kl sine 2la times l squared minus k squared. And from here, let's see, we're going to get that a e to the negative ika is equal to f e to the ika multiplied by cosine 2la, and then I want to combine the sine 2la's, so this is going to be plus sine 2la multiplied by, in fact, you know what, let's just do a negative at the front instead, so that everything inside becomes a positive, ik over l plus I over 2kl times l squared minus k squared. So this is going to become, if I multiply 2k over 2k, so this is going to be 2ik squared over 2kl plus I l squared minus k squared over 2kl. So this is going to simplify down. We're going to get that a times e to the negative ika is equal to f e to the ika times cosine 2la subtracted by sine of 2la multiplied by 2ik squared plus I l squared minus k squared over 2kl. Let's see. So up above here, we have f in terms of a, so we're going to reverse this relation. F is then equal to a times e to the negative 2ika, and we're multiplying by 1 over this entire thing. Cosine 2la minus sine 2la times, let's see, we can move the I out, and we can, yeah, multiplied by I times 2k squared plus l squared minus k squared over 2kl. Then f is then equal to, at the bottom is cosine 2la minus, I'm going to move this thing back here to the front. We have I times, let's see, 2k squared minus k squared is k squared plus l squared. Bottom is 2kl multiplied by sine of 2LA. And then at the top of this fraction, we have A times e to the negative 2IKA. And if I double check with the actual answer that we're supposed to get right here, this is in fact correct. And with that, we have finished obtaining both transmission coefficients, and then we move on to the final part of this problem. Okay, so for the final part of this problem, we want to confirm equation 2.172, which is the transmission coefficient, or more specifically, as Griffiths gives it, the inverse of the transmission coefficient, which is going to be equal to magnitude A over F squared. The standard transmission coefficient is magnitude F over A squared. So if we look at this, we have that, whoops, where is my pen? There it is. If we look at this, we have F over A is equal to e to the negative 2IKA divided by cosine 2LA minus I times k squared plus L squared over 2KL times sine of 2LA. So if we want to take the inverse of the transmission coefficient, we take A over F instead, and this is going to give us cosine 2LA minus I times k squared plus L squared over 2KL times sine of 2LA, and we're taking all of this and dividing by e to the negative 2IKA. If we then take the magnitude squared of this, then we get T inverse 1 is going to equal, immediately this bottom term goes to 1, because if you take the magnitude squared, then you're multiplying by e to the positive 2IKA. Those just go to 1. At the top, we have cosine 2LA minus I times k squared plus L squared over 2KL times sine of 2LA. And we're multiplying by cosine 2LA plus I times k squared plus L squared over 2KL sine 2LA. And immediately, hopefully you see that this is just A minus IB, and over here this is A plus IB. And when you multiply something by its complex conjugate, this just goes down to A squared plus B squared. So T inverse is just going to equal cosine squared times 2LA added with k squared plus L squared squared over 2KL sine squared 2LA. And my apologies, the bottom is not 2KL, it's 2KL squared, which is going to be 4k squared L squared. Okay. So from this point, in order to get everything in terms of energies and potentials, we need to make the substitutions. So for scattering potentials, we have that K is defined as the square root of 2ME over H bar, and we have that L is defined as the square root of 2ME plus V naught divided by H bar. So then we can do some calculations here beforehand. K squared plus L squared is going to equal 2ME plus 2ME plus V naught over H bar squared, or collecting terms is going to equal 2M over H bar squared times 2E plus V naught. Is that correct? Yes. Okay, so if we then square this, K squared plus L squared squared is going to equal 4M squared over H bar to the 4th times 2E plus V naught squared, which is going to be 4E squared plus 4E V naught plus V naught squared. Similarly, 4 times K squared times L squared is going to equal 4 times 2ME over H bar squared times 2ME plus V naught over H bar squared, which is going to equal 16M squared E squared plus EV naught divided by H bar to the 4th. If we plug all these in, then what we're going to get is that the inverse transmission coefficient is going to equal cosine squared 2LA plus, let's see, 4M squared over H bar to the 4th times 4E squared plus 4EV naught plus V naught squared multiplied by 1 over 4K squared L squared. So this is going to be 16M squared E squared plus EV naught at the bottom over H bar to the 4th, and we're multiplying finally by sine squared 2LA. From this point, we can do some simplification. This is going to give us cosine squared 2LA as always, plus, let's see, the h bar to the fourths cancel, the 4m squared cancels with this, makes a 4. So we have 4e squared plus 4e v naught plus v naught squared over 4e squared plus 4e v naught sine squared 2LA. And from here, we can see that we can pull out one of these terms, and this is going to give us cosine squared 2LA plus, and we can move this and say 4e squared plus 4e v naught over 4e squared plus 4e v naught plus v naught squared over 4e squared plus 4e v naught times sine squared 2LA, and this term is just going to become 1. In that case, what we get is that cosine squared 2LA plus sine squared 2LA plus v naught squared over 4e squared plus 4e v naught times sine squared 2LA. By trigonometric identity, this one just becomes 1, so therefore we're left with t inverse being equal to 1 plus v naught squared over 4e squared plus 4e v naught sine squared of, and let's add the L, so this is going to be 2a over h bar times the square root of 2m e plus v naught. And let me just double check that this is all correct. T inverse is 1 plus v naught squared 4e e plus v naught sine squared 2a over h bar 2m e plus, yeah. So if we look back up at what we're supposed to get, which is this right here, our expressions do indeed match. Therefore, we have proven the transmission coefficient, and with that, we are done with 2.32.